All right, so let's talk about series. So here I have a sequence of numbers, and in fact this is an arithmetic sequence. The common difference is 2, so I add 2 each time. So that's a sequence. All a series is instead of just a list of numbers, we're going to add each one of these terms together. So instead of commas between them, I'm going to put plus signs between those. So this is a series, and in fact this is an arithmetic series. All right, so all I'm going to do is add up each one of those terms. So in this case, if I add 1 plus 3, I get 4, plus 5 is 9, 16, 25, 36. So the sum of that series is 36. Notice a little trick here. Instead of just adding from left to right, I can add in any order because addition is commutative. So this is a neat trick. If I add up the 2 in the first term and the last term, I get 12. Then if I add these 2, I get 12. If I add these 2, I get 12. So 12 plus 12 plus 12, that's 3 times 12, or 36. All right, so here I have this arithmetic sequence where I've added up 1, 3, 5, 7, 9, 11. All right, so there's nothing wrong with writing all this whole series out like this, but what if you had a series that had 100 terms in it? It would get kind of laborious to write out 100 terms with plus signs between them. So what we do is we use this little symbol as a shortcut for writing out all the terms. This is called sigma notation. This is just a Greek letter called sigma here. So this is sigma notation. All right, so this is how this works. So this K is just a counting device. It's just like a little counter. And our counter is going to start at 1, and it's going to go all the way to 6. Okay, so we're going to let K start at 1 and go to 6. So 1, 2, 3, 4, 5, 6. So we know there's going to be 6 terms in this series. All right, so here's how it works. So first of all, I'm going to pretend that K is 1. So I'm going to put a 1 in for K. So 2 times 1 is 1. No, 2 times 1 is 2. 2 minus 1 is 1. So my first term is a 1. And then I know I'm automatically going to have a plus sign there. All right, so now K will be 2. Okay, so if K is 2, 2 times 2 is 4. 4 minus 1 is 3. And I'm going to have a plus. And now K is going to be 3. 2 times 3 is 6. 6 minus 1 is 5. So I know I'm going to have a 5. Now K will be 4. 2 times 4 is 8. 8 minus 1 is 7. There's my next term. Now K is going to be 5. 2 times 5 is 10. 10 minus 1 is 9. So I get that. Now K is going to be 6. And 6 is where we stop at. So it's the last term. 2 times 6 is 12. 12 minus 1 is 11. So I get that. And the sum of all those we've already figured is 36. So this is just a shorthand notation for writing out all the terms of the series. All right, let's look at another example of sigma notation. So I know this is going to be a series. That's what the sigma notation means. So I'm going to add up each one of the terms. How many terms are going to be in this series? So you have to be careful. You might just look at it as this number up here and say, well, there's 4 terms. But notice that in the previous example, we started with 1 down here and went up to some number. I believe it was 6. So we had 6 terms. But here we're starting with 0 and going to 4. So we've got 0, 1, 2, 3, 4. So there was going to be 5 terms in this series. So you have to be careful. Sometimes people will start with a 1 here. Sometimes they'll start with a 0. You just have to be really careful. All right, so let's do it. So n is my counter, and it's going to start at 0. So I'm going to shoot up with a K here. That should be an N. Sorry. All right, so if I start with n is 0, 3 times 0 is 0. 0 plus 2 is 2. So 2 plus. Now n is going to be 1. 3 times 1 is 3. 3 plus 2 is 5. 5. Now n is going to be 3. No, sorry, n is going to be 2 now. I better make a list or I'm going to get messed up. So I'll start with 0, 1, 2, 3, 4. So I've done 0 and I've done 1. Okay, so now n is going to be 2. Okay, so I'm going to put a 2 in. 3 times 2 is 6. 6 plus 2 is 8. So we've done that. Now I'm going to put a 3 in. 3 times 3 is 9. 9 plus 2 is 11. And then finally, I'm going to put in the 4. 3 times 4 is 12. 12 plus 2 is 14. And then I'm going to add all those up. So remember our trick from last time. It's easier to add the first and the last and get 16 plus another 16. That's 32. And 32 plus 8 is 40. Or you could just add straight across. 2 plus 5 is 7. Plus 8 is 15. Plus 11 is 26. Plus 14 is 40. All right, so the sum of that series is 40. Okay, notice some things. This is an arithmetic series because I have a common difference. My common difference is 3. Each time I'm going up by 3. Notice, right there's the 3. 3, remember 3 is like the slope, or the common difference is like the slope in the arithmetic sequence or series. So this is a linear equation. My slope is 3. My common difference is 3. And notice when I start with n equals 0 as my counter, this told me the original term or the first term, just like the y-intercept does in a linear equation. So arithmetic sequences and series are very much like linear equations. All right, so here's an interesting question. What is the sum of all the integers from 1 to 100? So I want to know what's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus all the way up to 100. I want to add all those numbers together. All right, if we wrote that out in sigma notation, so I want the sum, and we'll start with 1. So we'll go n equals 1 all the way to 100. All right, what's my formula I need to put in here to get this sequence of numbers or this series? Well, my n is going to be 1, then it's going to be 2, then it's going to be 3, then it's going to be 4, all the way up to 100. So this is really easy. All I need here is an n. Okay, so this is a shorthand way of writing out all these numbers. So you can see this is a really big shortcut. Saves a lot of space to write this instead of all those 100 numbers out there. So again, just to check this, make sure you understand, n is 1. So I'm going to have a 1 there. Then n is 2, that's going to be 2, then it's going to be 3, then it's going to be 4, so really simple. All right, so I want to add up all these numbers. All right, so there's this famous story about this little kid at school, maybe 100, 200 years ago. And his teacher wanted to work on something else, so she wanted to keep the class busy. So she told all the students just to add up all these numbers. She thought that would keep the class busy for a long time while she did something else. Well, there was this one little smart aleck kid in the class that got the answer within just a few seconds of the teacher assigning the question. And how did he get it so quick? So most of the kids in the class, they just started adding it up. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. And it took them quite a while to get all of 100. But the one little smart aleck kid, he was really clever. And he looked at it like this. I can add the 1 and the 100 and get 101. I could add the 2 and the 99 and I'll still get 101. Like that. So the same trick we did before. And actually he was a little more clever. What he did was this. He added a second row back here. Or he added the same ones and he did it twice. So 100, 99, 98 plus 97. He did all of that. So he added up the numbers twice. But notice, if he adds these two, he gets 101. Then he gets 101 again. Then he gets 101 again. all the way out to here where he gets 101. All right. How many of these 101s does he have? Well, he's got 100 of them, right? Here's the first one starting with 1. There's the second one starting with 2, all the way up to 100. So he has 100 101s. So he's going to add all these guys up 100 times. So he's going to have 100 101s. So 100 times 101. All right. You've got 100 of these things. You're adding the 101 up 100 times. You're multiplying 100 times 101. But remember, he had 2 copies of them. So he needs to divide his answer by 2. So 100 divided by 2 is 50. So 50 times 101, would be 5050. So 5,050. And he was able to get that answer really quick. All right, let's see if we can find a general formula for the sum of the first n terms of an arithmetic sequence. So here is that written down in segment notation. So I'm going to start with k equals 1, and I'm going to go all the way up to some number n. So say you had 5 terms in your series, the n would be 5. So it would be from k equals 1 up to 5. Here just any number n. So if k is 1, I'd put that there, and I would have a sub 1. And k is going to be 2, so plus a sub 2, plus a sub 3, plus a sub 4, plus all the way out until we get to a sub n. So if you had 7 terms in your series, the n would be 7, and we would go all the way out to a sub 7. All right, so we want to find the sum of the first n terms of an arithmetic sequence. All right, so how can we do that? Well, we're going to try the trick that the little smart aleck Gauss did, and we're going to write a second copy of these. All right, so what I'm going to do is write the same series backwards. So I'm going to start with a sub n, and then I'm going to do a sub n minus 1, a sub n minus 2, plus on and on and on until I get to a sub 1. So the exact same numbers, I just wrote them backwards. You can add up numbers in any order. So now I can add those 2 together, and these 2 together, these 2 together, and they will always be equal, as you saw in the previous example. Right, so when I do that, I'm going to have a sub 1 plus a sub n, so the first term and the last term. And you see here you have a sub 1 plus a sub n, and all these other guys will be the exact same. Okay, so how many of these am I going to have? Well, I've got 1, 2, 3, 4, 5, up to n of them. So I've got n of these. So the first term plus the last term, and I've got n copies of that. But notice I've done it twice. I've added these numbers together twice, once here and once here. So I need to divide that by 2. So we have a formula now. Get rid of that. So we have a formula now, general formula, for the sum of the first n terms of an arithmetic sequence. All you have to do is add the first term and the last term, multiply by n, and divide by 2, and you'll know the sum. All right, here's just a fun question. So I want to find the sum of the first 20 terms of this sequence. Okay, so this is a linear equation, so we know we're going to have an arithmetic sequence. All right, so let's write out some of those terms. So the first term, a sub 1, would be putting a 1 in for n, get 0. So the first term is going to be 3. The second term, putting a 2. 2 minus 1 is 1. 1 times 2 is 4. 4 plus 3 is 7. You get a 7. The third term, put in a 3. 3 minus 1 is 2. That's 8. Plus 3 is 11. Fourth term would be 12. That'd be 15. Fifth term would be 16 plus 3 is 19. All right, and you see what's happening here. My common difference is 4. I go up 4 each time. So it's an arithmetic sequence. My first term is a 3. Common difference or slope is 4, so I'll go up 4 each time. All right, what's the 20th term of this sequence? Dot, 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 all the way up to the 20th term. Right, so all I have to do is put in a 20. 20 minus 1 is 19. 4 times 19 is, let's see, 4 times 20 would be 80, so that'd be 76. And 76 plus 3 is 79. So the 20th term would be 79. Right, we want to find the sum of all 20 of these. So instead of commas, I'm going to have plus signs. So I want to add all these guys up. So I could just start adding. 3 plus 7 is 10, plus 11 is 21, but that's going to take a while. I could do Gauss's little trick and add the 3 and the 79 and get 82, and plus another 82, and do it like that. Or I could just use this simple formula that we got by doing Gauss's trick. So let's do that. So this formula says all I have to do is add the first term and the last term. So that's 3 plus 79, that's 82. I need to multiply that by n, that's 20, that's how many I have, and divide by 2. 20 divided by 2 is 10, so I have 10 times 82, which is 820. So the sum of the first 20 terms of that sequence is 820. All right, let's look at another example of a series. Okay, this example we know is going to be a geometric sequence because I have an exponential function. My variable k is up here in the exponent. So this is an exponential function. I know I'm going to have a geometric series. All right, so let's write this out. So I'm going to do the sum of the first 5 terms. So k is going to be 1, so I'm going to put a 1 in here. 1 minus 1 is 0. 2 to the 0 is 1. 3 times 1 is 3. So my first term will be 3. Then I'm going to put in a 2 for k. 2 minus 1 is 1. 2 to the first is 2. 3 times 2 is 6. Then k is going to be, I already forgot, starting with 1, 2, now it's going to be 3. So 3 minus 1 is 2. 2 squared is 4. 3 times 4 is 12. Now my k is going to be 4. 4 minus 1 is 3. 2 to the third is 8. 3 times 8 is 24. Now my k is going to be 5. 5 minus 1 is 4. 2 to the fourth is 16. 16 times 3 is 48. So notice this was a geometric sequence. I went 3, 6, 12, 24, 48. It's a series because I'm adding all the terms together. What's my common ratio? So what am I multiplying by each time? Well, it's 2. 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. 24 times 2 is 8. So my common ratio is 2. Common ratio is equal to 2. And you can see it's right there. And of course, my first term right here in front is right here. All right, so let's add these together. Now, so let's try the trick that we did last time. So 3 plus 48, that's 51. 24 plus 6 is, oops, that's not 51, that's 30. All right. So it doesn't work anymore. That trick doesn't work. That only worked for arithmetic sequences. Okay, so you can't just add these up like this and get the same thing every time. All right, so let's just add straight across here. 3 plus 6 is 9. 9 plus 12 is 21. 21 plus 24 is 45. And 45 plus 48 is something. I'm going to be lazy. 45 plus 48 is 93. All right, so to find the sum of the first n terms of a geometric sequence, you could just list out the sequence and add up all the terms. Nothing wrong with that. But it would be really cool if we had a nice formula like we did for arithmetic sequences. So let's see if we can find one. So here I have the sigma notation for the sum of the first n terms of a geometric sequence. This is geometric because my variable k is up here in the exponent. I have an exponential function. So let's start with k equals 1. Put a 1 here. 1 minus 1 is 0. R to the 0 is just 1. So my first term is a sub 1, just like we wanted it to be. Okay. My next term then, I'm going to put a 2 in for k. 2 minus 1 is 1. R to the first is r. So I have a sub 1 times r. Times r, not raised to the r. Let's try that again. So r. All right. And now my k is going to be 1, 2, and that's going to be 3. So I put in a 3. 3 minus 1 is 2. So I get r squared. So I have a sub 1 times r squared. All right, now my k is going to be 4. 4 minus 1 is 3. So I have r to the third times a sub 1. And you see the pattern here, which you already know because you know what happens in a geometric series. Let's write out one more. A sub 1, r to the fourth. And I'm going to keep doing that until I get a sub 1, r to the nth power. No, that's not right. My last one, I'm going from k equals 1 up to n. So n will be my last k. So k will equal n at the end. So if I put an n here, I'll have n minus 1. That's my last. So the first n terms, my last one will be r to the n minus 1. All right, so we have this. Now we're going to pull off this beautiful trick that some really smart person thought to do, way smarter than me. We're going to multiply both sides of the equation by r minus 1. Okay, so I'm going to multiply this side by r minus 1, and I'm going to multiply this whole entire side by r minus 1. Okay, that's legal to do. Nothing wrong with it, so let's do it. It should be fun. All right, so if I multiply this whole side by r minus 1, I have to distribute. So I have to take the r and multiply the r by every single term in here, all the way to the end. All right, so really slowly and carefully, let's see if we can figure out what that is. So r times a minus 1 will just be r, well, let's try it the other way. It'll be a sub 1 times r. R times this term will be a sub 1 r squared. Then it'll be a sub 1 r to the third. And then a sub 1 r to the fourth, and so on. Until we get to the last one. And if I multiply r times this one, r to the first, n plus 1, this will just be r to the n. So I have a sub 1, r to the n. So notice the exponent on r went up by 1 on each one of these. So this was n minus 1, so now it'll actually be n. Right. Now I have to take the minus 1 and multiply it by every term over there. All right, so let's do that. So if I multiply minus 1 times this, I'll get minus a sub 1. I don't know where to write this out. Well, we'll go out here. No, let's write it here. Minus a sub 1, and then minus a sub 1r, and then minus a sub 1 r squared minus a sub 1 r cubed, all the way to the last one. So plus dot 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 minus, well, we can say that's a minus with a plus. And the very last one then will be minus a sub 1 r n minus 1. I think we got all that. What a mess, right? That's a mess. But something really, really cool happens now. Notice that these guys cancel out. A sub 1 r minus a sub 1 minus r. So do these guys. They cancel out. These guys cancel out. And this one will cancel out with one that's right there that I didn't write. But you basically only have two left. You have, so equals, you have minus a sub 1 and minus a sub 1 r to the n minus 1. Those are the only two that are left. Sorry, I messed up right here. I did not pay close attention to what I was doing. I'll try this again. R to the n minus 1 is over here to the left of this. It's less than r to the n. So actually, let me write this out. There's an a sub 1 r to the n minus 1 right here that will cancel with this guy. Right, so those actually cancel out. And this will be the only thing that's left. Right? R to the n minus 1 should be over here on this side. So it cancels with that. So this is the only one that's left. So I'm sorry, that should just be an n. This is a mess, right? All right, so now those will be the only two that are left. All right, so now I'm going to clean this up a little bit. So I'm going to get rid of all this mess that we've done here. And just write out our final, or the final result that we got so far. So this is equal to minus a sub 1 minus a sub 1 r to the n. Right, so I'll just copy this up here. All right, so notice in both these terms I have a minus a sub 1, so I'm going to factor those out. So if I factored out the minus a sub 1, that will leave me with 1 plus r to the n. All right, so I got to back up a little bit. I made another mistake in there. There's a lot of stuff going on here that's messy. I messed up a little bit. All right, so let's go back and let's fix where I messed up. I had one of my signs wrong. All right, so I've multiplied all this by r minus 1. So let's go through it again. So I multiply the r by each one of these terms. So I get a sub 1 times r, a sub 1 r squared, a sub 1 times r to the third, times r to the fourth, r to the fifth, and so on. And my last one will be a sub 1 times r. Because if I multiply r, or it'll be r to the n. Because if I multiply r to the first times r to the n minus 1, 1 plus n minus 1 is just n. So my very last one is plus a sub 1 r to the n. Now, if this is r to the n, you're going to have an r to the n minus 1 right before it. You have to have. Because the one right before this was r to the n minus 2. Now it's r to the n minus 1. All right, so I have all this written out. And I had this written right the first time. I just ignored it. All right, now I'm going to multiply everything by the minus 1. So I get minus a1 minus a1r minus a1r squared all the way up to minus a1 r to the n minus 1. All right, so now those cancel, those cancel, those cancel. They all cancel up to there. So here's what I'm left with now. This one and this one. Right, so equals minus A1 plus A1 R to the n. When I did this a minute ago, I had a minus right there. I didn't pay attention and I put a minus instead of a plus right there. So got to be really careful with what I'm doing. All right, so that should be a plus instead of a minus. You can go back and change that in your notes. All right, now let's clean this mess up. So I'm going to get rid of all this and just leave ourselves with what we have here. So I have minus A1 plus A1 R to the n. All right, now, good. All right, this guy was what we were originally trying to find without this. So I need to divide both sides by r minus 1. So our final answer, the sum of the first n terms of a geometric sequence is equal to this. So minus A1 plus A1 R to n over r minus 1. All right, so now we have ourselves an answer here. And we're going to clean this up just a little. I have an A1 in both those terms, so I'm going to factor that out. So I'll have A1 times R to the n minus 1. Right, I did it backwards. So if I distribute this back, I get A1 times R to the n, and I get minus A1, which is there, over R minus 1. All right, so finally, after all that mess, we have a general formula for the first n terms of a geometric sequence. Okay, I'll never ask you to go through all that proof again, but here is a nice formula for it that we can use. All right, so let's try an example here. So let's find the sum of the first 6 terms of this sequence. So the first thing to do, let's write out the first 6 terms of the sequence. So if we let n be 1, 1 minus 1 is 0, that'll be 1, so my first term will be 4. We know this is going to be a geometric sequence because this is an exponential function. All right, my second term, 2 minus 1 is 1, so that'll be 3. 4 times 3, that'll be 12. So my common ratio looks like it's going to be 3, and we already knew that. So to get the next term, I'm going to multiply the 12 by 3, and that gets me 36. Then I'm going to multiply by 3 again, and I'm going to get a calculator out at this point because I'm lazy. So 36 times 3, my next term will be 108. And then I'm going to multiply that by 3, and I'll get 324. 1, 2, 3, 4, 5. I need one more term times 3, 972. All right, so I want the sum of the first 6 terms. Well, here's the first 6 terms, 1, 2, 3, 4, 5, 6. All I need to do is add those up. So I could just pull out my calculator and add those. It wouldn't take very long. If I had 100 terms in there, it might take a while to do it. But I could just add all these up one after another. It wouldn't be too bad. But just for fun, let's use our formula. All right, so what is my a sub 1? What's the first term? First of all, let's put plus signs between all these. So plus, 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 plus. All right, my first term is a 4. So we'll put that in here. And then my common ratio is R, which was 3. So I'm going to have 3. My n is 6 because I'm doing the first 6 terms. Minus 1 all over. My common ratio was 3. 3 minus 1 is 2. I get that. All right, let's ask our calculator what that is. So 4 times 3 raised to the 6 minus 1 divided by 2, and I get 1456. You can put that in your calculator and check and make sure if you're right. All right, let's actually add those up and see if that's what I get, because I don't really believe it. So let's actually just add these up. So I'm going to get on my calculator here. 4 plus 12 plus 36 plus 108 plus 324 plus 972. Hey, I get 1456. So if I just add all these up, I get 1456. If I use the formula, I get 1456.